This is a charged species. If somebody, I'll do probably one or two more after this if somebody's really excited about something. Okay, so what I would do is do it for copper. Okay? So the previous noble gas for copper for the electron configuration is, yeah, and to make it straight, here's what I totally recommend, because people pick the wrong noble gas. Look at the number on copper, it's 29, so don't pick krypton, because it's bigger than that number. Okay? So argon. Okay, what's the next level after argon? 4s2, this is for neutral, and then 3d, how many over? It's 9, however, because we're in the copper column, remember the copper column and the chromium column have an exception. They always like to half fill the s orbital. Okay? Which again, it's in the book, in the reader. Okay, but now he asked about copper, Andre asked about copper 2 plus. And so, copper 2 plus, we pop off 2 electrons. You need to remember, again, the second exception to know. First exception, this is a great problem because it involves 4 exceptions. First exception is half filling in the copper and the chromium column. The second exception is when a transition metal loses an electron, it loses from the s first of its valence before the d. So that would be the 3d9. I lost first the s, then one of the d's. So copper 2 plus, 3d9. Okay? Okay, anybody want to do a second one? Raise your hand if you have one you want to try. I'll tell you if it just would be totally impossible, which is, there's a lot of things I cannot ask you on the table because it would be impossible to solve. But I'm happy to do another one if you have one. And this is fun, you can do it with your friends at home. You're like, Mom, pick an element. You can try to figure it out after your mom picks her element or his element or whatever. Grab some. This one. Okay. So want somebody else? Yes. The white right there.
Chlorine minus.
Which one did you pick?
Chlorine minus.
Chlorine minus. Okay, chlorine minus. Now, if it's not a transition metal, it's probably a little bit easier just to figure out, if you add an electron to chlorine, what element are we talking about? Argon. Okay, that's your answer. Okay, good. I can do another one because that one wasn't bad. Yeah, way in the back there, way.
Iron 3 plus.
Iron 3 plus? Is that what you said?
Yes.
Okay, so iron neutral is, what's the previous noble gas? Anybody? Argon. And then it fills the 4s2, 3d, is it 8 or something? Oh no, 3d6. Okay, now we're going copper 3 plus, or iron 3 plus. So argon, we're losing both s's first, and then the d, 3d5. Okay? Well, I can do one more. You want me to do one in the F? Okay, here's where I couldn't actually pick anything.
Question.
I had to pick one that will work. I can do number 64 will work. Yes, 64. I can do gadolinium. What was your question? Yeah.
If you gave us on like the test that argon 3d10, you technically be copper 2 plus, or like
Oh, yeah. On a test, if I gave you the electron configuration and you had to work backwards, multiple elements would work because they'd have the same electron configuration. That's why Cl minus wants to be Cl minus because it's like argon. And that's totally fine. I'd have to be more specific if I want a particular answer. Which when I've done that on exams, that's what I've done. Okay, this one, what's the previous noble gas? Again, look at the number. That's the easy way. 64, what's less than that? 54 is xenon. Okay, I know that 2 is less than that number 2, but I'm looking for the previous lesson. Okay, now, after xenon, I go into what S level? It looks like I go into the 6S, right? 6S2. Okay, let me get a periodic table out. Okay, if you're not in my class and your instructor hasn't told you this, prepare to freak out. Okay. This table is not the same as the table up on the board. You see that? Okay, what fills after 6S2? Not F. The 5D1 fills, and then we go down. 57 fills before going down. You see that? So it's 5D1 is next. 3, 4, 5. Okay, let's write that down. Then what fills? Then F fills, right? Okay, what level F is this? 4F. How many? 7. Okay. That's the answer. Okay? Any questions on this? Now's the time to ask a question. These periodic tables don't totally work for the F block. Okay, hold up. Yes, we'll pan over. Yes, Zoe. Okay, ask me in a moment. Yes. How did I know I needed to put 1 in 5D? Because that was the next element in my periodic table. 57 is sitting in the D's. It's not sitting in the F's. It's in the D's. Don't look at this table. They're garbage. Okay? The next one is here. Okay? All right. But I need them for later, so they're not bad. All right. There was another question. Yes? There's many exceptions in the F orbital which we're not learning Exam II. Yes? Yes? Does the order matter of writing the orbitals? We more care about orbital, we more care about the order before you get to the F's. When you get to the F's, it gets a little messy. So in this case, I would not care if you flip-flop some of these. That would be fine with me. I don't know about the other instructors. Yes? Why is it 4F? For F, what is L equal to? Anybody? 3. So the lowest energy F orbital is 4F. So the first one's 4. Okay. All right. Oh my gosh, we're running out of time. Okay, what was your question? Okay, ask me after. Okay, that's too crazy right now. I cannot think about such things. Okay, now I lost my order sheet. Here we go. Okay, I have to pick only one last one. What do you want to do?
Titration.
Okay, so that did not work. That did not work at all. Stop. Okay, you pick a chapter, I'll have you vote. Who wants a chapter 5? Okay, who wants a chapter 6? Who wants a chapter 7? Okay, now, we're going to choose these 3. Who wants wavelength? Who wants Heisenberg? Who wants Rydberg? Okay, now I know what you guys want. Okay, we're going to do Rydberg right now. And then, we're only going to do 5 more minutes, and we're going to stop for specific questions. So hang in there. Don't be loud and get up yet. Just hang for 5 more minutes, even if you're bored. I would be bored too. Okay, so, according to the Bohr model of the atom, we have these orbits, which is n equals 1, n equals 2, n equals 3, etc. These are orbits. This is n, the same n as before, not moles n, but the other n. Electrons can be on these orbits. Electrons can also, if an electron is here, jump up orbits or come back down orbits. Okay? When they come down orbits, what happens? Energy is given off in the form of light, sometimes visible, sometimes not. Okay? And so you can calculate the energy either absorbing to cause an electron jump or falling, given off for causing an electron fall. Okay? And so you can calculate these energies, you calculate wavelength, you can calculate the frequency. How do you do that? There's two equations given in the text. The Bomber one I don't like at all, so I use this one. This one really doesn't have a name in the text, so I named it myself. I should have named it after myself, actually, now that I think about it. But I've named it the Rydberg equation because this is the Rydberg constant. Okay? And so this is the energy. This is paired with the following two equations, h nu and with hc over lambda. That means, using this equation, you can find the energy or frequency, nu, or wavelength, lambda. Okay? And so all you really need to know is the initial and final, the departure and arrival gates for the electron. Yes? You'll be given all these equations, but in different forms. Like in our class, you'd be given this, you'd be given energy as h nu, and something like c equals lambda nu. So you'd have to substitute yourself. Okay. So, okay, yes, give me two whole numbers. Go. Okay, what's your question? That's true. You're going to find out in chapter 8, which we haven't got to, there's atomic number squared here. But we're only talking about hydrogen, so it's 1 squared. Z, capital Z is atomic number. So you'll see that in the next chapter. So we're ignoring it right now, because it's just 1. Okay, I still need my two whole numbers. 4 and 2, which one's first? 4 is first. So N initial, I just had a random person. It's not really random, it's meant to you right there. Give me a 4, and then Johnny Fun gave me a 2. Okay? So then you can just simply do this calculation as follows. Change in E is the Rydberg constant, which is 2.179 times 10 to the minus 18 joules. 1 over N initial squared, 4 squared, minus 1 over 2 squared. And again, what these mean is N initial orbit 4, falling down to final orbit 2. So if this is 4, it's like an electron going from 4 down to 2. Is energy released or absorbed in this situation? Released. So is thus energy going to be a positive or negative number? Negative if energy is released for a fall. It's negative. And you can see mathematically it would be a negative number here. Okay, this is something, whatever. And you compare this, say if you want the wavelength, you can say, oh, that's hc over lambda, this value, which is h 6.626 times 10 to the minus 34 joule seconds. I'll give you that constant, 2.9979 times 10 to the 8th is c, meters per second. I'll give you that constant over lambda. That would be your unknown, so you could solve for lambda if you wanted to, because everything else is there. You'd have to do some calculation cross multiplication to find that lambda. Okay, that lambda would tell you the wavelength of the light given off. The energy would tell you the energy given off when the electron fell the drop from 4 to 2. So that's what that would represent. This is the Rydberg equation. It doesn't get harder than this, but you just be able to make sure you can do this kind of, you can calculate fractions on your calculator, basically is what I want to make sure you can do. And do cross multiplication, you should be okay. Yeah? Okay, you can ask me that after. I'm going to dismiss now everybody who wants to go and doesn't want specific questions. Hope you had a good time. Take care, get the heck out of here if you don't want to stay. And in a couple minutes, those who want to stay, you can move up. And you can ask me specific questions about homework or whatever practice problems. I'll take your questions first. Okay, we'll give about 2 minutes for people to shuffle out. Oh, and if I didn't get to your question, you can ask that to your concept. That's perfect. Okay. What was your question first? Okay, when an electron changes in orbit, an orbital is a little different. An orbit is going around, orbital is like a reactant. Okay, if you had to identify the color of light, what you would do is solve for lambda or nu. Depending on, and we would have to give you on the exam an electromagnetic spectrum, which listed lambda or a nu numerically. And so if you find one of those numerically and look at the electromagnetic spectrum, you would see, oh, I just got 650. That's the red visible range. Okay? And that's how you would know. So you have to use one of those. Okay, next question. Raise your hand if you have one. Okay, I saw yours first. Practice exam you're talking about? Okay, she's talking about practice exam. Winter 2012 for exam 2, I assume. Let me find that. What number are you talking about when I eventually find this craziness? Winter 2012, 22C. Is this draw the electron configuration for orbital energy line diagram, that one? Are you in my class? You have to ask me later, because our class is not doing orbital energy line diagram for exam 2, we're having it for the final. But I can answer that after everybody's dismissed. Yeah. Okay, yes?
I had a question about one of the sample problems for the electron configuration.
Okay, earlier you mean?
Yeah.
Oh, okay, do you remember which one it was?
Yeah, it was anyone that, basically any of the ones that had charges, how did that get determined? Like, how do you, like, you know how in copper 2 plus you went from 4 to 2, 3 to 9 to 4 to 1, 3 to 10, like, how did you go to that?
Okay, is this okay?
Yeah.
Okay, assuming that you know this, he's wondering how do I get here? You start removing electrons. Each one of these superscripts represent electrons. So there's one S electrons, so there's 10 of the Ds.
Oh, no, I mean,
So how do I get here now?
no, I don't get the second part, where you went from 4 to 1.
Oh, you don't get this?
Yeah.
Ah, from here to here. Okay, so that's one of the two exceptions for the Ds. This is what you would think it is, but what happens is the Ds, in the 4th and 9th column, that's a chromium column, so chromium, moly, and then that's the copper column, copper, silver, gold, etc. Those have an exception where they like to only half fill the S, meaning only put one in the S, and then put the rest in the D. So if you take one out of the S, it's going to put from 2 down to 1, and this will 9 up to 10. So you just need to remember that. Okay? Yes? Does the exception apply only to transition metals? Yes. Otherwise, it removes the electron most previously added. Okay, next. Yes? Fall 12 practice exam. Let me find that. Fall 12. Number what? Number 18. Is that a redox with aluminum? Okay. You want me to just go through and balance it? Or was there a particular part that was difficult? Okay. So C, D, and E is what you're asking about. Is that right? Yeah, okay. Just wanted to clarify. So I gave this Al2O plus O2 goes to AlOH4 minus. We want to balance this. Well, aluminum, put likes and likes together. There's nothing that the oxygen can go in. Okay? Because I can't put aluminum down there because I would never be able to balance the aluminum because there's no place I add aluminum. So oxygen is all by itself, and when oxygen is around, or ozone, or a molecule containing oxygens, usually, this is not unusual, where oxygen will be by itself in the reactants products, usually reactants. So don't be surprised by this kind of stuff. Now, how do you balance this? It uses 4 steps. Step 1, balance whatever's not oxygen or hydrogen. So in the second reaction, there's nothing. Step 2, balance the oxygen with water. 2 waters. Balance the oxygen. Step 3, balance the hydrogens with H+. And then step 4, balance the charge with electrons. Okay? Yes?
At some point that if you're like water or oxygen, just ignore it.
What to ignore if it's in the original equation would be water, H+ or OH-. Anything added. Yeah, because you can't ignore O2 because it doesn't come back added in any of your 4 steps. You can only ignore 4 steps sort of thing. Okay, so for the top one, step 1, balance whatever is not oxygen or hydrogen, that's aluminum. 2, I need 2 aluminums on both sides. Step 2, balance the oxygens. There's how many on the right? 8, and the left 1, so I have to add 7 of those fools. 7 H2O. And then now step 3, balance hydrogens with H+. There's 14 hydrogens here. How many here? 8. So I'm going to add 6. Okay. What's the overall charge on the right-hand side? Left-hand side, 0. Step 4 now. Right-hand side has what charge right now? +5. I got +4. 6 minus 2. So that's 4, so +4 electrons. Okay, now we do this kind of stuff. 4 electrons, 4 electrons. Oh, that's easy. You just add. Okay, so let's just add it up. Wow, I gave it each one this quarter. No multiplying. Oh my gosh. Oh. This gets easier and easier. 2. Yeah. Most people got tripped up because there's 2 right here. What to do with the oxygen this quarter. There we go. There's everything. I wanted this in basics conditions. Oh, I can cancel a couple things. I can cancel the H+. There's 2 here. And there's 2 waters that I'll cancel to make 5 on the left. That would be the acidic conditions answer, the basic conditions answer. I'd have to identify that H+, there's 2, and add that number of OH minuses to both sides. So let's do that. That's +2 OHs minus +2 OH minus to both sides. And so you get 5 H2O plus Al2O plus 2 OH minus plus O2 goes to 2 AlOH4 minus plus 2 waters. Okay? Oh, 2 waters. And yeah. And then I would cancel out, my last step would be to cancel out the waters, which is 2 here, 5 here, so 3. Is that okay?
So when oxygen is by itself,
And when oxygen O2 is by itself, yeah, this will always happen. This is going from 0 to -2, yeah, it's a reduction. Okay, next. Yes? Oh, okay. You don't know how to, okay. Let me show everybody what you're talking about here. This is the back of an exam, typical exam for me, and I give you the table as promised. For the most part, there's nothing that you're going to do with them. They're there for fun. I could ask you, though, and you'll see on some exams, give me the wave function for a 2s orbital. In which case, that's the R2s times the y of the s. So I literally would write for 2s this. Do you see that right there? That for 2s times this. So I literally would write them next to it. That would be the wave function for a 2s. If I need the wave function for the 3s, I'd write this with this. Okay, see how that works? That is the most I could possibly ask you, and if you can literally copy it from the back page to your page, you got it. 3 2 points for copy. Okay. Next, yes? Do you have a page number for me? That might be easier. 8? 85.
83.
83. Okay, my goodness, up here. Okay, number 5 on page 83. Number 4 on page 83. You're talking about this one right here. Okay, I'm with it. I'm with it now. On it. Game on. Okay. It has I gave you this balanced. There's 20 liters of this. There's 5 liters of this. I want to know the amount of this form. Okay? So, this, anybody, is what kind of problem? This is a limiting reactant problem combined with what, I'll tell you, yeah, what you said. So, these two lead to moles, so I've overspecified right now. So I have to do 2 separate calculations. Okay? Now, because of the law of combined volumes, I can say, well, 5 liters of CH4 times 1 liter of CO2 divided by 1 liter of CH4 can easily tell me that there's 5 liters of CO2. So I can even do that in my head. Okay, and for the other one, 20 liters of CH4. There's 1 liter of CO2 for every 2, oh wait, the 20 went with the oxygen, right? Yeah. 2 liters of O2. So now I'll get 10 liters CO2. Okay? How much was actually formed, 5 or 10? 5, a smaller number. So it looks like it's C. Is that okay? Limiting reactants, also a smaller number. Okay, who's next? Yes? 84, number 11, same exam. Is this the one with the net ionic equation? That one? Okay. So in this case, it says, I mentioned this in class, but I can understand why you're like, what the heck? Because we haven't done a lot of these really. This is a net ionic equation. It's a double replacement. So you're going to say, oh, okay, I've got H2CO3 plus KCl. What you might not have remembered is this always automatically will convert to H2O liquid plus CO2 gas. It's an automatic conversion, whatever that species is formed. Now we can continue on with the problem. You'll find out this is aqueous, find out this is aqueous, and I think all this might have been given, yeah, this is aqueous. And so what you're going to find out is this is a good electrolyte, this is a good electrolyte, this is a good electrolyte, but liquids and gases are not good electrolytes. And so what's going to happen is the potassium will cancel out, and the chlorines will cancel. So you'll have what you'll see listed in, let me see if I can find it. It should be D, yeah. So what will be left after all those cancel would be HCO3 minus aqueous plus H plus aqueous goes to H2O liquid plus CO2 gas plus, oh that's it, which is D. Okay? Okay, next, yes?
Reaction over water.
Oh, yeah. Let's get back to that. A general overview, or what are you looking for? How to do it, or do you have a specific question in mind?
Maybe general overview and then do a specific problem.
Okay, if you can find me a specific problem, that would be totally ideal. But the general overview is, what happens is, When there's a reaction over water, there's some sort of reaction that occurs, and then a gas is a product. That's the key. And so what happens is there's this tube that takes the gas, and it takes it into a container that has water in it. But this container is special because upside down in this container is a like some sort of graduated cylinder or burette or something. And what happens is it's filled with water. But the water, as the bubbling occurs, and the bubbling bubbles into this, and it causes, I'll just make it bigger to show you. It causes a gas to fill up at the top. So the water level goes down, and you can now measure a volume. Now, that volume is going to lead you to do helpful calculations. There's two important formulas, and this is a subset of Dalton's law. Okay. So, the two important formulas are the total pressure, which often will be the barometric pressure. So atmospheric pressure, which could be given, or you just use atmospheric pressure. 1 atm, 1.01, 325 bar, whatever. Okay? Equals the pressure of the gas from the reaction plus what other gas is in here? There's water vapor, basically, from the water. So I'll put PW for water. Okay, now, this is atmospheric pressure. Okay? This one, PW, is from a table. You're going, what table? The table on the back of your exam. And it's called, partial pressure water is also called vapor pressure. So if you look on the back of your exam, based on the temperature of the room, you can look up this literal number right here. So that's from a table. All right, table. Table. And then P gas is typically what you're solving for. In a normal problem, that's what you're solving for. There's one more equation. The ideal gas line. Pressure of the gas times the volume equal the moles of the gas, RT. So basically the ideal gas law. So sometimes what happens is we have you solve for the pressure of the gas, put it in here, and then we ask you, oh, how many moles of gas do we have? That'd be a pretty standard problem. And all you do is subtraction here, put that number in here, you know every other number except the moles of the gas, and you find the moles. Sometimes we'll convert it to mass or whatever, but that kind of problem. It can also be done backwards, where I've also seen it where we give you the moles or mass, you back calculate to get the pressure of the gas, then you back calculate for one of these two. So forward or backward, but this is it. It's typically a pretty simple problem. Is that okay? Do you have an example, or that's good? Or okay, cool. Try that out. If you can't get it in the one you're looking at, you can ask me later. Yes?
Page 94.
Page 24. 94. Okay, what number?
24.
94, number 24. Okay? And this is the one with the ammonia and oxygen. Okay? This is a pretty tough problem. I will admit. Here's the reaction. So it's page 94, number 24, 4, NH3 plus 5, O2. I put this on here because it was on a previous final. I thought I better prepare you. So it was not my brainchild initially. These are all gases. Okay, there's the reaction. So here it says a weather balloon. Okay, useless information, blah, blah, blah. Initial volume of 10.9 liters. So the initial volume is 10.9 liters. All of the ammonium molecules react with all of the oxygen to form all this. That sentence is basically telling you there's no limiting reactant, and there's no reactant left. Nothing is left over from the reactants. Okay? That's what that sentence means. It says the temperature and the external pressure, hence the pressure of the balloon, are constant. That means ignore them. Okay? What is the final volume of the balloon after the reaction is completed? Okay? Assuming the balloon is indefinitely expandable. So what you would do is say, so things are changing, volume's changing, so this is a combined gas law problem. So you'd say, oh, combined gas law, that's this. Okay? But they just told you to forget about pressure and to forget about temperature. So this comes down to as follows. V1 over N1 equals V2 over N2. So far, so good? Okay. Now, at this point, you're still happy. Okay, now we plug in, and then the joy starts to disappear very soon. Okay? V2 is what we're looking for. Yeah, V2 is what we're looking for. You realize at this point, okay, V2 is what I'm looking for, but I don't know N1 or N2. Or at least at this moment you don't. This is where all joy, all hope is lost at this point. What happens is, I think I've explained this a couple ways. One way is in the book, but nobody, or in the reader, but nobody understands that. So let me try a different way. Okay. What's the initial amount of moles of the reactants? 9. 4 plus 5. Okay? If they're ideal gases, which is not stated, I don't think, but which is assumed in the question, we're all assuming ideal gases. We have 9. Because these are moles, they have the same volume and the same moles, etc. So 9 moles. Final? 10. So, technically, this is not how you do it, but I think it's easiest to understand. Technically, what you would do is call this some variable, and the reader calls it z, and then this would be 10 times z. Just to be more general, and then z would cancel out. But nobody gets that, so I forgot about that. Okay? And so now you can find V2. Is that okay? Okay. Cool. Next. Yes? Same exam. Number 10. And time is ticking, by the way. Because I have to go home and watch MTV and stuff. Number 10. What's the wavelength? For the energy content, that one? Okay. Equals hc over lambda, which is E is 550 kilojoules or 550 joules per mole. This is H 6.626 times 10 to the minus 34 joule seconds. C is 2.9979 times 10 to the 8th meters per second, lambda. Okay, now this is what I would really have to do on the calculator now. Or did you, if you cross multiply and solve for lambda, did you get a number there? That means I have to do it, which is cool. It'll just take me a little while here. If somebody gets it before me, please tell me. Or were you going to say something else? Yeah, we have to mess around with the moles, but I want the number first. Yeah. Oh gosh, how does this calculator work? Okay, minus 30. This is going way slower than I hoped for. Sorry to delay your problem here so much. Hold up. Within seconds of genius. Okay. Now I forgot what the problem was. Number 10? Yeah. Okay. What happens is, I wish I could go back on my calculator. Shoot. Okay, you get a really small number. Like 10 to the minus 31. Did you all get that? It's a really small number. Small. Okay. You have to get rid of the moles, you basically have to multiply that by Avogadro's number. Which helps you get rid of the moles. That's how you get rid of the mole unit. Is that okay? Okay. And then that's a small number, but less small, and you change that to nanometers. And you should get 218. Okay. I'll take one last question from the crowd. Yes, Priya, you win.
Where are the second nodes? I know that
Yeah, you want a 3p, x, y, or z? Z. If you were drawing a 3pz, n is 3, L is p, which is 2. And the nodes are n minus 1 or 2. So you're looking for 2 nodes. This is on the z-axis. The one node that you can see, let me see if I can find a different colored pen here. You can see the angular node, which is planar, goes through the middle. This is a node. Okay, there's one more hidden node, which is a radial node. And it's inscribed circle. This is the second node right there. It's called radial. It's within the orbital itself. Yes? That's right. I haven't taught that yet, but she or he is totally right. If I haven't done shading yet, I'm kind of saving it for chapter 10. If you don't on an exam, that's totally fine. If you do, that's fine too.